Hi, welcome to Chem 6161 stereoselective reactions. Today we will talk about the felkin model. Basically what we will see is what happens when we have a carbon group, okay, with a chiral atom in the alpha position of the carbon group, how this induces the stereoselectivity when we are adding a nucleophile to the how this addition of the nucleophile to a carbonyl group is determined the stereoselectivity by the presence of this alpha chiral center. Okay, basically when we do this reaction, the attack of a nucleophile to a carbonyl group, what we can have is that the addition takes place for the phase of the carbonyl group that is in front of the slide or from the phase that is behind the slide. And we get these two diastereomers. Of course, the key is how we can predict which is the major diastereomer of these two. In order to do this, we will do different models. The first model that we will use with this compound will be the steric model. Okay, I imagine that we have here, for example, the large group will be a phenyl, the medium group will be a methyl, and the small group will be a hydrogen. Okay? What we need to do? The first thing, we need to draw the Newman projection of this carbonyl. How? We will see the carbonyl in this way. Okay, if we draw in this way, we have here the carbonyl group, here the phenyl, and behind we have, if I saw like this, the phenyl is at my right, the hydrogen is at my left, and the methyl will be just behind the carbonyl group. Okay? This will be the Newman projection. Please, if you don't see how I convert this stereocenter in this one, please use molecular models. Okay? Next step. Well, I put the large substituent in perpendicular. That means I have two options. One is rotating in this direction and the other is rotating in this direction. And I will get two options. Okay, first here, if I move this phenyl here, the methyl will be in this direction and the hydrogen will be in this direction. If I just do the opposite, that means I put the phenyl perpendicular but in this direction, what I have is I rotate this and then the methyl is going down and the hydrogen is going up. Okay? Then what is happening? The nucleophile attacks the carbonyl group following the Burgitz-Zunitz trajectory. Remember that the Burgitz-Zunitz trajectory is more or less around 107 degrees. Okay? That means that the nucleophile will attack opposite to the side where is the large group, will attack following this trajectory. In this case, the nucleophile will attack following this trajectory. Okay? And then what we do is to analyze both trajectories. Here you can see that when the nucleophile approaches to the carbonyl group, what we have is a hydrogen. While in this case, when the nucleophile approaches to the carbonyl group, what we have is a metal. Obviously, this approach will be favored because a hydrogen presents less steric hindrance than not a metal. If this is happening, the product that I will get will be this one, nucleophile, OH, phenyl, and behind I will have methyl, phenyl, and hydrogen. Okay? And then the only that I need to do is to draw which will be the configuration. If the phenyl is here, if I draw it like this, the nucleophile is behind, the OH is in front, and then what I have is phenyl, hydrogen, methyl. Okay, importantly, this stereocenter is exactly the same in this because I didn't change it. Okay, I am only creating this stereocenter. And if I didn't draw it wrong, that I guess that not, that is right, this will be the final configuration of the major diastereomer. This will be the most favorable. Okay? Is only these steps. I have the aldehyde, I watch the aldehyde from one side, I draw the Newman projection, and then I put the bigger substituent perpendicular to the carbonyl group. I have two options. Okay, and then I analyze the Burwitz-Dunitz trajectory of the nucleophile, and I choose the trajectory that presents less steric hindrance, that in this case is this one because it's only having a hydrogen, while here I have a metal. Okay? This is one model. The second model that I will explain is when we have in the alpha position a group that can produce a chelate. We have a functional group that can produce a chelate. Okay, for example, I have this one. I have normally a heteroatom that can coordinate with a metal. In this case, for example, what I will do is I add a metal that can coordinate can form a chelate between these two oxygens, okay? And for example, I add a nucleophile like methyl magnesium bromide. Okay? The big difference between this example and the last one is that in this case, what will happen first is that the zinc or the metal will coordinate with these two atoms. That means that I will have this intermediate. Could be zinc, could be any other metal. We have a coordination. Okay. And if I put it like this, the hydrogen is here and the phenyl is here. Okay, this is intermediate, and then the nucleophile will attack in front of the slide, or from behind of the slide. Okay. Which approach will be better? Well, we have to check this stereocenter. In this case, because this is a 5-member ring that will be almost planar, what we will have? That in front of the slide we will have this hydrogen, while behind the slide we will have a phenyl ring. Which will be easier? Which trajectory will be easier? Which Burgit-Zunitz trajectory will be easier? Well, if it's in front, this nucleophile only sees the hydrogen, while if we are coming from behind, if the nucleophile is coming from behind, he faces this phenyl. Obviously, the approach for in front of the slide will be favored. In this case, this will lead addition of the methyl. Remember that the nucleophile is the methyl magnesium bromide. And remember that this stereocenter will remain the same as at the beginning. Okay? Right? Again, how I do this when I have a chelate element in the alpha position? First, I draw, as you can see here, I draw the two functional groups in the same plane and in the same direction. Okay, in this case, the two functional groups that will form the chelate will be the oxygen of the carbonyl group and the oxygen of the methoxide. Okay, then in order to put the methoxide in this direction, I have to rotate the molecule, and if I rotate the molecule, I get this stereocenter here. Okay? And then the only that I need to do is to add the metal to form the chelate. This is a fixed structure, a 5-member ring. And then I analyze the two trajectories, the two possible Burgit-Zunitz trajectories of the nucleophile. One in front of the slide, the other behind of the slide. The one that presents less steric hindrance will be the favorite. That means that this will be the major diastereomer. Okay? In this case, the diastereoselectivities are very high. Okay? Normally, a metal coordination forming this rigid intermediate makes that the diastereoselectivity is very, very high. Okay? This is the second method, is the chelate method. And what happens, that would be, this will be the last case, if instead to have a chelating agent, what I have is electron withdrawing group, like for example a chloride, but can be for example dibenzylamine. Okay. What happened? Well, in this case, we will use a polar model. Okay, and what I need to do is like I do it at the beginning. I have to watch the molecule from here, like I did in the first example. Okay, if I do this, in this case the phenyl is here, the chloride is at my right, and the hydrogen is in my left. Okay? I only draw the Newman projection of this. What is the next step? The next step, and this is very important, this electron withdrawing group, this chloride, this bromide, this iodide, is the one that has the priority and has to be perpendicular to the carbonyl group. Okay, that means I have two options, like I showed you before. I can put the chloride here, and then the phenyl is coming in this side, and the hydrogen is coming down. I only do a rotation. Okay? Or can be the chloride in the other side, chloride here, and if the chloride is here, what I have is hydrogen up, phenyl down. Okay, I am only rotating this carbon-carbon bond. And as I did in the first case, now we analyze the Burgit-Zunitz trajectory of the nucleophile. Okay, the nucleophile can attack in this way or can attack in this way. Always has to be opposite where we have the group, the functional group perpendicular to the carbon group. We have these two trajectories, and then the only that we need is to choose which trajectory will be better. In this case, again, here the nucleophile, when it's coming to this trajectory, he only faces one hydrogen, while in this case the nucleophile is facing a phenyl group. Obviously, by steric hindrance, this will be favored, and this, what we'll do is that we have the addition of the nucleophile, we have the wedge in this direction, the nucleophile in this direction, phenyl down, chloride, phenyl hydrogen, okay? And then the only that I need is to put it in the right drawing, phenyl, nucleophile, OH, and here I have the chloride, hydrogen, and this will be the major diastereomer that I will form in this reaction. Okay? These are the three models. We have the normal steric one, we have the chelate, and we have the polar one. Okay? As a summary, when we are facing an addition to a carbonyl group that has a chiral center in alpha, okay, I will put this example. I put ABC, the three substituents. The first that we need to ask is, do we have a chiral, do we have an electron with grabbing group in alpha? Okay, this is the first question that we have to do. If the answer is no, we have the steric model, the first that I explained. If the answer is yes, second question, is the electron with grabbing atom, electron with grabbing group, forming a chelate, or is able to form a chelate. If the answer is yes, what we are using is the chelate model. Okay, we coordinate a metal, we form a 5-member ring, and we analyze which trajectory is better. If the answer is no, we use the polar model, the last one that I explained. We put the electronegative atom perpendicular to the carbonyl group, and we analyze the Burgit-Zunitz trajectory of the nucleophile. Okay? This is basically the felkin model. Okay? How we can know which will be the major diastereomer when we are doing an addition of a nucleophile to a carbon group. Okay, it's something that some of you have been seen in the last semester or in last year. Okay, but if not, basically it's very easy. Please remember that always the most difficult thing in this lecture is to translate 2D to 3D, okay, the drawings to 3D. That means please use molecular models at the first times that you are trying to resolve the exercise, and you will see that when using molecular models you will gain a 3D vision and you will be able to do it only on paper. Okay? Thank you very much for your attention and see you in the next lecture.